So let's continue with the IPv6 security fundamentals and what kind of attacks we can do in the IPv6 world. There are quite a lot of things to cover. What we will focus on mostly in this presentation are the attacks at the local links. So in regards to neighbor discovery, IPv6 router-related attacks, MLD attacks will not be covered in this presentation. This will be covered in the other room where we will see where will be presented specific MLD attacks. There are quite a lot of other attack vectors regarding some of these extension headers, which will be presented after the lunch break here in this room to evade, for example, IDPS devices. We will focus on the first three here, with the exception of MLD, which we will not cover in this presentation. So from an attacker tool point of view, there are some penetration testing tools which are specifically for the IPv6 protocol suite, but there are, of course, our normal penetration testing tools like, for example, Metasploit or something like that, which also work under IPv6 or our IPv6 specific frameworks. Here you have just a list of different tools which can be used to attack specifically the IPv6 protocols. As I said before the break, we have the THC IPv6 toolkit, which was developed by Mark Heuser, which is just a Linux-based tool which can be downloaded under this URL. Then we have the SI6 IPv6 toolkit, which was developed by Fernando Gont, which is also here on the IPv6 Security Summit. And then we have Chiron. Chiron is an advanced tool developed by Antonius Atlasis, a good fellow of us, who has a dedicated workshop on how to use Chiron tomorrow. So if you're interested in some more advanced attack techniques and how to use this tool to launch these attacks, I highly recommend this workshop tomorrow. We will mainly use here the THC IPv6 toolkit because it brings a lot of tools to start all kinds of attacks. This is just for your references, just an excerpt of the tools included in the toolkit, and we will use some of these to launch the IPv6 specific attacks. Yeah, our goal, we will try to cover more or less wide range of IPv6 related attacks, which are most of them very common and well known, just for you in order to get the big picture and to be prepared. Okay, we will first have a look how these attacks are performed, and then we have a look, okay, what can we actually do about it and how can we mitigate those attacks? So let's start with the attacks on the local link in regards to neighbor discovery. There are two families of attacks. One related to the neighbor discovery process. So for the resolution of a given IPv6 address to an MAC address, you can attack the duplicate address detection mechanism, which will result in a denial of service condition for the client, which I will show you in a minute. And then we cover some attacks related to the IPv6 router discovery process, so with the router advertisements. So let's start with the neighbor discovery process. As we have seen in the Wireshark before the break, when the IPv6 stack gets initialized on a client, he has to validate that the IPv6 address he has configured is unique, and he's using the duplicate address detection mechanism for that. And as we have seen in the Wireshark, when he tries to verify the uniqueness of this address, he's using a special source address, the so-called unspecified address, : to validate the uniqueness. So what happens when a client receives an answer and that this IPv6 address is already on another host. Well, that highly depends on the operating system in question. For example, Windows-based boxes will try to configure another IPv6 address a couple of times. If all these duplicate address detection verification fails, it just gives up, and then the client has no IPv6 address at all, not even a linked local address, which basically is a denial of service condition, at least for your IPv6 connection. To do that, it's actually pretty simple just so that you know what the topology looks like. It's pretty basic. We have our legitimate router, R1, which is the white box on the table. We have our switch, which is also the white box. We have our legitimate client, which is connected to port 1. Let's call her Alice. And then we have the malicious attacker connected to port 2, which is the bad hacker H. They're all in the same VLAN, in the same broadcast segment. And this is just the basic topology, which we will use in the course of the demonstrations I will give. So let's have a first look at the denial of service condition in regards to the duplicate address detection. To do this, I have just a virtual machine, nothing fancy. It's just a Kali Linux where the THC IPv6 toolkit is already installed. And just let me. So, and the tool we want to use for the denial of service in regards to the duplicate address detection is just called DOS new IP6. When we see the description, this tool prevents new IPv6 interfaces to come up by sending answers to duplicate IPv6 checks. So when an IPv6 stack gets initialized and he's doing the address verification over the duplicate address mechanism, this tool just answers these packets, and then the client thinks, oh, there is someone who has already configured this address, so I have to configure another address because I can't use this address as it's already used by another host. So as you can see, pretty simple. You just say DOS new IP6 and just specify the interface. It's just ETH0. So what we see, he now is just listening to DAD packets. And as soon as a new client now gets connected to the network, he will answer these DHD requests. Let me just force that. So, give me a second. I've forgotten to configure a specific command on the interface that it comes up pretty fast. As you can see, now Windows tries to configure an IPv6 address, and then he detects, oh, there is potentially someone who has already this address, and then this nice network error comes up, well, informing me there is an IP address conflict. And as we can see here, my Windows client tries to configure different addresses, but every time he is doing the duplicate address detection, this tool here is answering. This is the prefix which I am using here on this box. And as we can see here, it's pretty interesting, even though I'm sending spoof packets for these three addresses. My Windows client tries to configure it continuously, but he will, of course, this will, of course, always fail. So let's have a look. How does it actually look on the interface? HDA 0. Let me just do it again quick because of the configuration I did. Change. No, actually I have to put up this. So, as we can see here now, he is initializing the IPv6 stack. Interesting. Just give me a second, because this doesn't work at all. Yeah, wonderful. So, what we can see here now is that the DOS new IPv6 tool is sending a spoof packet for a linked local address because the IPv6 stacks got initialized and my client tried to configure a linked local address. The tool was sending a spoof packet, and let's see how what the result is. Interesting. So he was sending a spoofed packet for this linked local address. Maybe he spoofed himself. Let me just check. Come on. I hate those virtual machines. No, it wasn't that one. It could be that it was this virtual machine. For E6. No, actually it wasn't at all. So which system did you spoof? Interesting. Yeah, the demo gods were not with me this time. For 3EE. Interesting. There shouldn't be any other besides the Windows box, which it isn't. My box. Yeah. Wonderful. It seems that it was my USB device, the USB Ethernet. And just to double check, just that I don't tell you anything what's not the case. Yes, wonderful. Now, sorry for that. As you can see here, I have a USB to Ethernet adapter, which is bridged into one virtual machine and connected to a separate port here. As we can see here, IPv6 and IPv4 is enabled. So this interface should configure himself a linked local address. But when we have a look here at the parameters from the interface, we see now, even though IPv6 is enabled, and as soon as IPv6 is enabled, this interface should have at least a linked local address. But as we see now, it doesn't have any IPv6 address because Windows just gave up. When we look here at the toolkit, interestingly, the interface here got initialized. It tried to configure this IPv6 linked local address. The duplicate address detection for this address failed, and then just he gave up, which just basically means, from an IPv6 point of view, this interface is not usable anymore. So you really have to now flap the link so that IPv6 gets initialized again, or you have to stop it and then you have to reinitialize the interface. Let's just see if that's the case. We just stop the attack. I will just shortly deactivate IPv6 and activate it again. So the attack is not running anymore. And let's have a look at the IP configuration of the interface. It should now have everything it should have. Yeah, as we can see now, because I stopped the attack and reinitialized the interface, now everything is working as expected. And as we can see here now, the link local address is the DE89, which is exactly the link local address which the tool spoofed, DE89. So he spoofed the link local address, and then IPv6 isn't working on the interface anymore, because without the link local address, IPv6 just isn't working on the interface. So as we can see, pretty simple to do. Yes, I know there's a conflict. And with the impact that at least for your IPv6 connection, this results in a DOS conditional. Pretty simple. You just have to be inside the layer 2 domain, just launch this tool, and the tool just listens to these DAD-related packets. He can distinguish between normal packets and the DAD packets, because all DAD packets have the unspecified source address, : and these are sent to a multicast address. So from a switch point of view, this packet gets transmitted on every port which is inside the same broadcast domain or inside the same VLAN. And as soon as the tool sees a packet, it just sends a response, which basically means this IPv6 address is already in use. And then, as we have seen, this interface just gives up after after configuring one link local address, and as I said, this results in the denial of service condition, which is actually quite interesting, because I have already seen it on this device that he tries to configure more than one link local address. I wasn't able to verify why does it behave so now, but typically for the link local addresses, it tries to configure 8 addresses in total, and if all 8 address verification mechanisms fail, then he will give up. I'm honestly surprised that he just tried it once and then gave up, but the result is potentially the same, and which just results in the denial of service condition. Question?
From an attack's point of view, to react to neighbor specifications, I need to target that multicast group.
No, yes, sure.
So how do you know in advance which multicast groups I need to be part of? I think isn't this dependent on the target address?
It's dependent on the target address, but the tool is or was coded in such a way that he will just that the stack will just accept every packet destined to any multicast address.
Okay, but if I've got a switch which is small enough to distribute multicast in a...
So you mean that the multicast-based packet gets only forwarded to the actual port where the end host is connected? Well, unfortunately not. The problem is, and there is some feature which is called MLD snooping. The basic idea behind this is that the multicast-based packets do not get flooded to all ports inside one VLAN, but only to that port where the actual end station is connected. And with this snooping feature on the switch knows which multicast group is behind which port. But the problem is this MLD snooping feature does not work for link local multicast addresses. It would work for global multicast addresses, but for all link local multicast addresses, even if you would have configured this snooping feature, it would not work. So the link local multicast-based packets get forwarded to every port residing in the same VLAN, regardless of the snooping configuration. Yeah, you're welcome. So as we can see, pretty simple, and from an IPv6 point of view, results in a denial of service conditional. Just the only hard requirement is that me as an attacker, I have to be in the same layer 2 domain as my target system. That's all I have to take care of. As soon as this is done, I just can passively listen to these DAD packets, answer to them, and all new IPv6 hosts which are connecting to this network will have no IPv6 connection at all. So the next one, neighbor solicitation advertisement process. This is the process to get the MAC address to a given IPv6 address. Same principle as in the IPv4 world, where we had ARP request and ARP reply. In the IPv6 world, we have a neighbor solicitation for a specific address, and the answer is the neighbor advertisement. In the IPv4 world, we had an attack called ARP spoofing, where you were able to create a man-in-the-middle situation between two hosts which are sitting on the same VLAN. And the basic principle applies to IPv6 as well. Instead of sending spoofed ARP replies, I'm just sending spoofed neighbor advertisement in order to ensure that the neighbor cache of my target system gets poisoned, so that there is a false false information from IPv6 address to MAC address, so that from a layer 2 perspective, my client is not sending the frames to the actual MAC address, to the destination, but it is sending it to me. I can, of course, then just forward or just activate IP forwarding, and then I will be a man in the middle, just like in the IPv4 world. So, and in order to do that, another tool inside this THC IPv6 toolkit is called Parasite 6. As you can see here from the description, this is an ARP spoofer for IPv6, redirecting all local traffic to your own system or Nirvana if fake MAC address does not exist by answering falsely to neighbor solicitation requests. So the legitimate clients are sending neighbor solicitations to resolute the MAC address to a given IPv6 address. The attacker here just answers to these neighbor solicitation requests with a fake MAC address, and from a layer 2 perspective, all Ethernet frames get forwarded to me. I can read them in Wireshark, and as long as I have IP routing configured on the box, I can transparently forward the frames to the actual destination, and so I have a transparent man-in-the-middle situation, just like in the IPv4 world. Same principle applies here, and as we can see here from the syntax, it's pretty simple. I can create a denial of service conditioner when I just insert here a fake MAC address, or I just, of course, can use my actual MAC address of the interface, so that on layer 2, all frames get forwarded to me. So let's just do that. So we have here an optional minus lowercase l loops and resends the packets per target every 5 seconds. Because from an attacker's point of view, I want to ensure that the poisoned entry in the neighbor cache of my victim does not get replaced by the legitimate MAC address from the target. So I can loop the packets every 5 seconds just to ensure that the entry in the neighbor cache where the IPv6 address from the destination and the association to my MAC address never gets deleted from the neighbor cache. Same example or same procedure like in the before world. And as you can see, -L interface, ETH0, and I can use a fake MAC address. Let's just use one. Or let's just use my actual MAC address. So that's my MAC address from the interface. And now I'm saying parasite 6, please loop the packets on interface ETH0, and please use this MAC address. Yeah, and as you can see here, just as a note, when you want to transparently forward the packets between the two victims, you have to enable IP routing or IP forwarding. If not, it just results in a denial of service condition. The packets or the frames gets forwarded to you, but the attacker does not forward it to the actual destination. As we can see here, started ICMP neighbor solicitation interceptor. And now we see here he is sending a spoof packet to this link local address for the default gateway, because the clients try to get the MAC address of the default gateway, and he is just answering these neighbor solicitations with spoofed neighbor advertisement, so that in the neighbor cache of the victims, that the association between the IPv6 address of the default gateway, FE80::1, is associated with my MAC address. And as we can see here, he spoofed also a packet to the actual router. And he is now doing that as long as this is running. So let's have a look. He spoofed a packet to FA80:43EE. I know that is my actual Ethernet interface on my host system. No, that's my Wi-Fi. Here's ETH0, 43EE. So that's the link local address of my wired connection. Not this one, not the USB one, the native one. So let's have a look at the neighbor cache. How it looks like. So we have here an association from FE80::1 to 000C9FA6. And as we can see, that's the MAC address of my attacker. So again, pretty simple. You really don't have anything to do. The only requirement is you have to be, of course, in the same layer 2 domain. And as soon as that is done, just fire up this listener, I would call it, or this interceptor. And because all these neighbor solicitation packets to get the MAC address are multicast-based packets, from a switch point of view, they get forwarded on every port for this layer 2 domain. So you will always see these packets, and you can't do anything about it, even when you would configure something like a snooping feature, which we discussed a couple of minutes before in regards to MLD. This would not work. Link local multicast-based packets are always forwarded on every port inside that VLAN. And you see, it's not rocket science. It's actually pretty simple from a configuration point of view, or using the tool. pretty simple from the syntax, with quite devastating impact from an IPv6 point of view, because by just launching this and enable IP forwarding, you will be a man in the middle and can read transparently every traffic transmitted between two hosts. And I can, of course, spoof one client sitting in the segment, and I can, of course, spoof the router so that I'm just, even if the traffic gets transported over a layer 3 boundary, the return traffic, which is sent from the router, gets forwarded to me. I can just read it and forward it to the actual destination so that my two victims, it's completely transparent for them, and they do not even recognize that they get spoofed or are victim of a man-in-the-middle attack. Same procedure, same principle like in the IPv4 world. Because in the mid-90s they thought, hey, the local link is trustworthy, so we do not have to perform any means of authentication or anything else to secure this exchange, which results exactly in this problem. Yes?
Previously mentioned public key where there are stopless spoofing.
Well, it would, yes. Technically or theoretically, yes, it would. But from a practical point of view, it will never get implemented. But it would stop the attack, yes. We will cover that. We first will have a look, okay, what are the actual problems inside the local links? And then we will cover, okay, what can we do about it? Because that's quite important from a securing point of view. So, but as you've seen, pretty simple. Nothing really, it's not rocket science at all. Yeah, as we have seen, this attacks against duplicated address detection for the denial of service conditioner, for the link local addresses, for the global unicast addresses, and these duplicate address detection has to be performed for all unicast addresses, be it configured over the stateless address configuration mechanism where the prefix is inserted in the route advertisements, be it when the address is assigned over DHCPv6, or of course when you configure it statically. But when you configure it statically and you have an IP conflict, well, then you have to reconfigure it manually, of course, because there's no automatic measure in any case which would generate a new one. Yeah, and attacks against the other nodes, as we have seen, either for denial of service condition or for a man-in-the-middle positioner, just send spoofed neighbor solicitations or reply with spoofed neighbor advertisements to neighbor solicitations which the attacker received, because these neighbor solicitations are directed to a multicast address, so he will see these multicast-based neighbor solicitations, and he can just answer with a spoofed neighbor advertisement. Yeah, or he just can unconditionally send unsolicited spoofed neighbor advertisements to a given target, which also results in the same either denial of service condition or a man-in-the-middle condition. But man-in-the-middle is typically this what you want to do, because you want to transparently be a man-in-the-middle between two end hosts to just read the packets which are transmitting between those. Yes, besides the THC IPv6 toolkit, you can of course use Scapy doing that. Scapy is a very powerful tool where you can craft any packet actually you want to do, and you need a little bit to get used to Scapy, but from my point of view, I love Scapy, and you can craft any IPv6 packet that you want, and you can of course loop that all, so you can specify everything you need to achieve the same goal, but the more time-efficient method would be just using THC IPv6 toolkit. Yeah, and this we have seen. He's just starting the listener or the interceptor, and then he's just spoofing the packets. So we can use Gapi, of course, for that, but this is just for your reference, so that you can, when you want to play around in the lab and you don't have the THC IPv6 toolkit, you can, of course, use or craft your own packets to do the attack. And as already said, you need to enable IPv6 forwarding, otherwise it will result in a denial of service condition. So basically, from an attacker point of view, nothing has really changed in the IPv6 world. We have the same problems, ARP spoofing or neighbor spoofing in the IPv6 world. We have a couple of new attack vectors in regards to the duplicate address detection, but technically we had the same issue in the IPv4 world, where a client has to do the same with gratuitous ARP packets. So basically, in regards to the neighbor discovery process, we have the same problems like in the IPv4 world. So, but as I have mentioned before the break, we have a new process in the IPv6 world, that is the router discovery. So that the client actively tries to find a router by sending a router solicitation, and then receives a router advertisement where specific information are placed inside. So, and you could guess it, of course, these packets aren't authenticated either, because we are all brothers on the local link. And from an attacker's point of view, you can, of course, interfere with that pretty easily. So there are basically two big problems, or the problem statement is more or less that the router advertisements are a fundamental part of the IPv6 DNA. And deactivating this approach or behavior might result in not expected behavior. So one potential approach could be, well, I just deactivate the processing of router advertisements on my local clients, which can be done configuration-wise. But this, of course, leads to the fact that you have to configure the default gateway on every client manually, and you generally don't want to do that. As I said, you can do it with 10 clients, 20 clients, but as soon as you have to manage more than 50 clients, it gets really cumbersome. So at least for client operating systems, that's not an operational feasible way to prevent these kind of attacks. But let's first have a look, okay, what can happen? Basically, you have to differentiate between two attacks. So some are generating entity accidentally active in your network. For example, one of your employees is bringing his Fritzbox or whatever Zoho router into your network. He plugs it in, and there's IPv6 configured. The box starts to send router advertisement, and the clients will process the router advertisement and will configure an IPv6 address accordingly, and of course a default gateway. In the earlier days, this was also the case for Windows-based systems as soon as you activated internet connection sharing, because the Windows box thought, well, internet connection sharing is activated, so I will act as a router, so I should send router advertisements. In the meantime, Microsoft changed this behavior, and they released a knowledge base article and a fix for that, so that even though when you activate internet connection sharing, it does not start to send router advertisements per default, or just a virtual machine running something which just sends router advertisements. This could happen, of course, or when the bad attacker wants to interfere with the router discovery, either to create a denial of service condition by sending many bogus router advertisements, and each of these router advertisements has a couple of prefixes included, which then results in a denial of service condition because the client operating system, he's processing the router advertisement, sees, okay, there are a couple of prefixes, so I have to configure my interface identifier. And when you have quite a lot of them, the client operating system is doing nothing else than configuring addresses. And this results in a denial of service condition, which is for the whole box, not only for IPv6, for the whole box. Or, of course, traffic redirection, when I'm sending spoofed router advertisements. When I just send periodically spoofed router advertisements, the clients install a default route and will potentially use me as a default router for every traffic going to another layer 3 subnet.
Sorry, just
Yeah, sure.
Then our service many bogus router advertisements, that's not just IPv6.
No, that's for the whole box. Box, yes. But to be fair, this issue was discovered by Mark Heuse back in 2010, and every major operating system vendor was affected by it, and every major networking vendor was affected. So basically, everyone was affected by it. In the meantime, at least Unix and Linux-based systems and the networking devices, as long as you are running not an ancient image on it or an ancient kernel version, this problem is fixed. In the Microsoft world, Microsoft had an interesting standpoint regarding this issue. It was discovered, as I said, 2010, and Microsoft said, well, no, we won't fix that. That's intended behavior of IPv6, so deal with it. And the funny thing is, at the beginning of 2013 or end of 2012, they released an IPv6 readiness update. They call it readiness update. It's not a security update in any case. And in this readiness update, I just go a little bit forward just to see what this is. This article states, this article introduced the IPv6 readiness update for Windows 7 and Windows Server 2008 R2. Issue number 2. If you use many address and IPv6 routes, the kernel memory is exhausted and CPU usage reaches 100%. This update limits the number of advertised prefixes and routes that each interface can process to 100. Well, yes, this mitigates the issue, but not completely, because he still has 100 addresses on the interface. I will show you in a second. And from an IPv6 point of view, imagine I have 100 IPv6 addresses on any given interface, and I want to initiate a communication to any given destination. Which address should I pick as a source? So they did something, but from my perspective, not in a sufficient way. But we will come to that. So let's just start with the traffic redirection by spoofed RAs. And as you can imagine, there's, of course, another tool inside the THC IPv6 toolkit for that. Oh, this resolution of the beam is awful. So, and how is it called? Fake router 26. So if we have a look, we can see we have a couple of things we can configure. And what we have to configure is a network prefix with the mine uppercase A. And we have, of course, again, define the interface where the spoofed route advertisement should be sent. So before I start that, just to give you a better picture of that. So as you can see here, now I'm actually capturing from my Ethernet interface. As you can see here, we have router advertisements. These are the valid router advertisements which are sent from the white box here on the table. As we can see here, from the FE80::1 to the linked local multicast address. And it has a PIO, prefix information optional, this prefix. So if we look at my configuration on the box for my Ethernet interface, I should have now, as you can see, an address from this prefix or two when we are including the temporary address. And we have a default gateway, FE80::1. So that's the normal and intended behavior. So, and one interesting thing is in the IPv6 world, when you read default gateway, you would assume, well, okay, an IPv6 client or a client in general can have only one default gateway. Well, in the IPv6 world, this is not necessarily the case. So when I will start to send these spoofed route advertisements, we will see that we will here have another default or another gateway. In the IPv4 world, we just have one. In the IPv6 world, we can have many on the interface. Which one is then used as the actual default gateway? This has to be verified based on the local routing table on the client. So let's just start this attack and let's have a look. So I just say, okay, fake router 26. I have to specify the prefix, the prefix information which should be announced in the faked router advertisement. I just say, okay, 2001 DB8, let's just call it dead beef, /64, and please send it over ETH0. So as we can see here, he's starting to advertise the router or the router advertisements. When we have a look again at the Wireshark, where do we have it? Let me just quickly filter so that you can see it better. Type 134 are router advertisements. And as we can see now, as soon as I started the attack, we have now two entities sending router advertisement. We have, of course, our legitimate router sending the periodic route advertisements, and we have another device, which is actually the virtual machine, the Kali Linux. And when we look here, what is inside this route advertisement, we see, okay, we have the prefix information, the prefix which I configured on the command line. And this gets sent periodically on the local subnet. So let's have a look. What are the consequences on my IPv6 configuration on the interface? Let's just do it that way. Yeah, as we can see now, here on my wired connection, I have now 4 addresses on the interface, 2 from the legitimate prefix and 2 from the spoof prefix. So here's my legitimate prefix, the DB81, and the spoof prefix, the DB8 dead beef. And, surprise, we have 2 default gateways, which is interesting because the word default gateway implies, okay, I have 1 and not 2. So, and the order here is not an indication which of these linked local addresses is actually used as a default gateway. So, in order to verify, okay, which one of these linked local addresses is used as a default gateway, I have to have a look in my local routing table on my box here. So, when we have a look, so what do we see here? I mean, I have more than one default route, but the interesting ones are the ones on interface number 15, because that's my ETH0 interface. The other ones come from the Wi-Fi network, which is connected here to the conference network. And I'm also using FE80 as the default gateway. But when we have a look here at the interface 15, we have the FE80 default route pointing to FE80::1, and we have another default route to FE80, yada, 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 both going over the same interface. But the interesting part is, if you're looking at the metric, they're different. So, and the lower the metric, the better this default gateway is. So in this special case, my client, when he would send a packet destined to another subnet which has to traverse the default gateway, he would not send the traffic to the legitimate router. He would send it to the actual attacker. Now you may ask yourself, okay, why is that the case? Why does my local client prefer the spoofed gateway and not the actual gateway? Well, That's actually pretty easy to answer. We have in these router advertisements, we have several flags which can be set. And the one responsible for this is the so-called default router preference. The preference is just can be set to low, medium, high, 3 values. And this is an indication for the clients which default router, for example, he should use. And as we can see here, my legitimate router hasn't set anything, so it just transmits the router advertisements with a default preference of medium. But the toolkit is setting this default router preference to high, which means the client receives 2 router advertisements, one with preference medium, one with preference high, and he will prefer, like the name implies, the information he got from the router advertisement with a high preference. So, and of course I can configure the preference on the specific interface. Just make sure it's actually VLAN 20. I can of course manually set it to high, which you should always be doing. This at least helps against the scenario where you have, for example, the Fritzbox, which accidentally one of your employees plugs the Fritzbox in. It sends the router advertisement. This configuration at least prevents that your clients will prefer the router advertisement sent from the Fritzbox in comparison to your legitimate router. It will not help against any other router advertisement-based attacks. So, but let's have a look what happens now. As we can see here now, after I have configured it, here is my legitimate router advertisement. And as we can see here, the router preference is set to high. And we have our spoofed router advertisement, which is also set to high. Now, any idea what my client is now doing? Well, yes, at least in the Windows space, as we can see, we have now 2 default routes over this interface. Here, this one again, same as before, but they have the same metric now. And what is my Windows client now doing? Per packet load sharing. Wonderful. That's nothing I want really to have. But he's using one route for one packet. For the other packet, he's using the other route. So, I mean, from an attacker point of view, I just get 50% of the packets, but in the end of the day, it results in a denial of service condition because at least for every traffic which has to pass the layer 3 boundary, so the router, he only gets half of the packets. So I can set it to high. It will help against devices which are accidentally brought into your environment, but it will not help against any attacker who wants to interfere with your IPv6 configuration or your IPv6 setup. But as a general rule and a general best practice, you should always configure the router preference. I mean, this here is for Cisco, but you should always ensure that you manually set the router preference to high. Always, without exception, just to make sure that if someone brings in your device and he starts to send router advertisement, that at least your router advertisements gets preferred before the accidentally sent router advertisements. So, basic rule: configure on every interface which is IPv6 enabled, configure the router preference always to high. And as we can see, when we can't see it because I can't see a router advertisement in the Wi-Fi network up until now, but we should have an indication. Yes, we have. As we can see here, interface 17 is my Wi-Fi connection, which is connected to the conference network. And in here it has a metric of 41. That's just Windows internally, Windows always prefers wired connections over wireless connection for whatever reason. So he has a metric of 41, but it does not have the metric of 266, which would be the default metric for the default preference. And as I've taken care of setting the router preference to high here on the conference network, at least I try to protect my IPv6 configuration so that no one is sending spoofed router advertisements. I mean, there are some mechanisms how you can do that anyways, but we will cover that in a minute. So this is actually the first attack, just sending periodically spoofed router advertisement, and if you do not have configured a router preference too high on your legitimate router, it will result in a man-in-the-middle scenario for traffic which is passing the layer 3 boundary. It has no effect for traffic passing between two clients inside a local network or inside the broadcast domain VLAN, because they are not using the default router. But as soon as traffic gets over the layer 3 boundary, the client will use the attacker as a default gateway and will forward all packets to the attacker. Question? You're looking? Okay. So either man-in-the-middle position or denial of service when you just do not forward the packets which have to cross the layer 3 boundary. So the second, more devastating attack is just the flooding of router advertisements. So before I start that, I don't know the proper translation, but ich will mir nicht den Ast absägen, auf dem ich sitze. Sorry. I will deactivate IPv6 on my box just to ensure that my box does not crash during the attack, which would be not that good. So I will deactivate IPv6 on both interfaces. But
Is your box running a kind of update?
yes, it is. But not necessarily, but at least during the attack, the CPU load will spike to nearly 100%. But when I stop it, my system will recover. Without the update, the system will stay at 100% forever. And that's the reason, just to make it more smoothly, I have deactivated now IPv6 on my host machine for both interfaces. But I have a wonderful Server 2008 machine. Let's just verify layer 2 connectivity. This looks good. As we see, he was, of course, also a victim of the faked router advertisement, as this Windows server has now 2 IPv6 addresses from different prefixes and 2 default gateways. But I'll just shortly disconnect it and connect it again, just so that we have a clean configuration when it will open. Come on, I've given you more than 2 CPUs and more than enough RAM. Don't be so sluggish. So, just shortly deactivating and activating it again. So we should have Yeah, this looks good. I will start the task manager up front, otherwise I may not be able to do so. So, everything normal. The virtual machine is just idling, has 2 CPUs, and more than enough RAM. As you can see, I've given her 4 gig of RAM, which should be sufficient, and 2 CPUs. And now, what I will do is just flood the network with route advertisement. I will close Wireshark, otherwise the GUI will just crash because of the amount of packets he has to display. And there's another tool called FloodRouter26. So, and as you can see here, pretty simple, again, from a usage point of view. In the simplest sense, you just have to specify the Ethernet or the interface, your network interface, and then you're good to go. And we will just do that. As you can see, every dot printed are 1,000 packets, 1,000 route advertisements. So I'll just stop it. So, and we should have an immediate. So, yeah, the task manager is still showing 0%, but the only reason is because I can't do anything at all inside the virtual machine. As you can see, I tried to do anything, but it just crashed more or less. I mean, it will recover slightly when we have luck. There we go. As you can see, the CPU usage spikes to 100%. I already stopped the attack, and it will stay there forever. We actually tested it a couple of years ago with the new laptop from my boss, from Enno. It was 8 cores, 16 gigabyte RAM, and we did test it. Tuesday evening, we did the attack for 30 seconds. We stopped it. We went home, came back on the next morning, and the box was still running on 100%. So it will stay there forever. And we have luck. We can actually use it a little bit. So now issuing the ipconfig command, you see it will take a while. And as I said, in each transmitted router advertisement, there are different prefix informations. So ideally, we will see now, or in a couple of seconds, that this interface has a lot of IPv6 addresses. I hope so. Yeah, wonderful. As you can see, these are all the addresses the client, this box, has now configured on his interface. And this CPU usage will stay, as already said, on 100% forever. You have to either reboot the box or completely disconnect the network interface and reconnect it again so that you can use it. And as you can see, quite a lot of IPv6 addresses on the interface. And well, it might be usable more or less, but if this is any system who has to perform, or which has to perform a specific function, I wouldn't trust that it can do it now again, or at all. So, as we can see, the CPU spiked to 100%, and every operating system vendor was affected by that. Just to give you an comparison, I will just shoot the virtual machine in the head pretty quickly, otherwise it will take forever. So while it is rebooting, yes, I know. As you can see, the consequences are quite devastating in regards to the CPU load. But Microsoft released this readiness update, and I will now activate IPv6 here on my interface. Yes, I want to run you. So here, I hope you can see it. We see here the CPU usage. Now I have in total 8 cores. So let's do that again with a machine which installed the patch. What you can see now, it's much slower than before because my client, of course, has to process now these route advertisement packets, which of course results then in less CPU power for the virtual machine. But CPU usage 40%, which is quite a huge bump in comparison to before, where I had 4. But as you can see, I still can use it. It is still working. But as you can see, I have quite a lot of addresses, but they're only limited to 100, as I have installed the patch. But still, 100, well, there's no real use case where you would use 100 IPv6 address on any given interface. So they could have reduced it to 5, and it would be sufficient from my point of view. But they didn't. They said, okay, for whatever reason, they decided it should be 100. But the main point is, when I stop the attack, the CPU load drops again. Okay, I have still 26%, but I assume this is just because of the virtual machines, which are running in parallel, of course. Let's see which process is consuming it. As we can see, 12% from the VMware VMX daemon. So I can use it during the attack. It uses more CPU load, but as soon as I stop the attack, the system recovers. So you should absolutely install this update, but it is only a recommended update. So it depends on your Windows update policy if you are, whether or not you are installing recommended updates or only important or critical ones. If you do not install recommended updates, you most likely won't have this update installed, but you should do it. So, but from an IPv6 point of view, this still results in a non-deterministic behavior of the IPv6 protocol stack on my client here, because I still have all these addresses on the interface, and I have to flap the interface in order to remove all those IPv6 addresses. As I've said, at least from an IPv6 point of view, don't expect that this system behaves like it should, just because of all these addresses which are now configured here on the interface.
So what would you use as a temporary source address when it's sent package from here?
Well, that's a good question. I don't know. I mean, we can try it. Let's just. Well, the problem is when I'll now.
If you send a ping packet from this machine, would you just a random one from there?
I suppose. I mean, if the destination address is in the same prefix as an address configured here on the interface, it would of course use that temporary address. But you cannot predict which of these source addresses he would use when you would communicate to a system distant or in the IPv6 internet. So there is no deterministic behavior to say, okay, even though I have 100 addresses configured, I can say, okay, he will use this one. That's, at least from my observation, totally random, and he will just pick one of them. Yeah, absolutely. And this is actually the biggest issue in regards to attacks on the local links, messing or tampering with the neighbor discovery process to gain a man-in-the-middle positioner, and flooding the network with these router advertisements, which, as I already said, was an issue discovered back in 2010, and every networking and operating system vendor was affected by this issue. In the meantime, Linux and Unix are all fixed for several years. Networking vendors, Cisco, fixed it pretty quickly, I think in about 3 months. Juniper wasn't that quick. Juniper said, well, yeah, okay, we recognize this as an issue, but we will wait for the IETF until the IETF specifies some countermeasures to mitigate this attack. In the meantime, it should be fixed, but I haven't verified it with actual Juniper gear. But hopefully it is fixed.
Sorry, one more question.
Yes, sure.
What happens when on a Linux system you do this block?
Well, he just,
drops everything?
yes, it is a rate limiting, basically implemented. I think he will take the first 3 or 5, and everything which comes after that in a specific time frame, it just gets dropped. So a much better implementation than in the Windows world or from Microsoft, because 3 to 5 is more than sufficient for your normal IPv6 operation. Yeah, and these are the 2 biggest issues we have in regards to IPv6 or IPv6 security on the local link. So now the questions arise. Okay, actually, yeah, this is the CVE which was released. Windows does by randomizing route advertisement prefix. You see it's dated back to 2010, and it took Microsoft 3 years until they released a patch which softens the consequences. Yeah, as we have seen, and as we have tested this with the laptop from Enno, the Windows was actually under the impression, well, I don't have any active networks adapter anymore during the attack. And as we can see here, this box had 8 CPU cores and 16 gig of RAM, so quite a powerful machine, but it was still running on 100%. So it's not the issue that I'm running it in a virtual machine. It doesn't matter. The performance of the machine doesn't matter as long as you do not have this update installed. He will peak at 100% every time. So there are some attacks against DHCP-v6. But they are the same like in the IPv4 world. What problems did we have in the IPv4 world? That someone is running a DHCP server and advertising address information to your client. And basically, we have the same problem in the IPv6 world. When you're using DHCP-v6 and someone is running a DHCP-v6 server, he can assign addresses from a different prefix to your clients. But luckily, or depending on how you look at it, he is not able to provide a default gateway because there is no such option in DHCP-v6, but he can just use the router advertisements to provide the default gateway. So basically, from a DHCP standpoint, it boils down to the same problem we have in the IPv4 world, that someone unintentionally or maliciously has a DHCP-v6 server running on your network and is issuing addresses for your legitimate clients. Yeah, to boil it down, same problems and same mitigation techniques like DHCP-v6. So now knowing, okay, what could all possibly go wrong, now we should talk about, okay, how can we actually mitigate those issues, or are there any mitigation techniques to prevent those kind of attacks? Actually, this is quite unfortunate, but defending against those attacks is actually pretty hard. Why? We will see in a couple of minutes. But we will have to deal with the situation anyway. I will just skip that. On a client operating system, you don't have any possibilities to circumvent those issues. So as in the IPv4 world, we have to rely on security controls implemented on our access layer switches to mitigate those attacks. in the IPv4 world to mitigate ARP spoofing. We had a feature, at least in the Cisco space, called Dynamic ARP Inspection, which is used to prevent ARP spoofing, and it will boil down to the same mitigation techniques or approach in the IPv6 world, so that your first hop switch has to provide those features. And Cisco is the marketing term for all these security features, is Cisco First Hop Security, short FHS, which was released in several waves and included all kinds of mitigating techniques for several attacks. And the first, or phase 1, was released in the summer 2010. And the first major feature they released was, or is called, Router Advertisement Guard. Basically, what AR Guard is doing, it's just filtering router advertisements which are coming into a specific interface. It basically behaves like a stateless ACL, which filters the router advertisements. So in our scenario here, and luckily the white switch in front of us does support it. In our case, we can configure RR Guard or RA Guard on every interface besides the interface where the actual router is connected, because he should send, or the router advertisement sent by the router should be forwarded to the clients, but not from any other port. So what we would do is we would configure RR Guard here on this port. So even though when I try to send the router advertisement, the switch will just drop the router advertisement. Sounds good in principle and works more or less. And the configuration is actually pretty simple. So just give me that I did not anything wrong, or do not anything wrong. Where do we have it? So I just want to verify which interface is bridged to which physical one. We have that 0 is bridged to this, and 8 is bridged to that. So this is bridged here. Wonderful. So what I will do now, I will configure Router Advertisement Guard on the physical link where the attacker or the virtual machine is connected to. In this case, it is port Gigabit Ethernet 02. And from a configuration point of view, it's pretty simple. You just say, okay, IPv6 ND for neighbor discovery, RA Guard, and you are good to go. So configuring that, and now let's try whether or not the attacks work with this feature enabled. So let me just verify. I will just quickly deactivate it just to make sure that I have a clean IPv6 configuration. So it's enabled. Wonderful. Interesting. So that's an interesting one. Actually, yeah, thanks. Well, I should do it. Yeah, thanks. So link local address, so wonderful. Our normal behavior, router sending router advertisement, I configured the addresses, I have a default gateway. So this should also apply to the Windows box, which should have rebooted up until now. Well, technically, yeah, you could be right. Okay, then just do it again. Yeah, this may be the case. Oh, thanks for that. So, but as I said, pretty simple mechanism to configure. Basically on every port where your legitimate router is not connected, and as we have seen, pretty simple configuration-wise. So, no, don't want to activate it now. Maybe later. Just forgot the key at home. Sorry for that. So this looks good. So he receives the legitimate router advertisement, so everything is working as expected. So, and now I will go back to the attacker and start the flooding again. Well, just for demonstration purposes, I should have deactivated v6 on my here, so that is just so that we have a better performance. So, and here we go again. So this shouldn't have any impact on the other virtual machine because it is connected to the port Gigabit Ethernet 01, and I have configured router advertisement guard on Gigabit Ethernet 02, where the Kali machine is connected. So, looks good. So we see when we open the task manager, see, nothing happened. So the switch just discarded the packet. But it's a little bit unfortunate because there's actually no indication in the switch logs that he did filter anything. He's doing it, as we have seen, but when we look at the logs, there isn't any indication that this feature dropped anything, which is a little bit unfortunate because from an operator point of view, I generally want to know when some client is flooding the network with router advertisements. I want to know it so that I can have a look, okay, why is this happening? So, but as we can see, it is working as expected. We have configured the feature on this interface. We started the flooding of router advertisements again, and the switch filtered the router advertisement, and they will not get forwarded to my victim, to the Windows Server 2008. Sounds good, but problem is that all these first-hop security features can easily be circumvented by the use of fragmentation. So it is kind of cat and mice. So Mark Heuse discovered this vulnerability. Cisco implemented router advertisement guard, and then Mark put a little bit thought into it. Okay, is there any way to circumvent all these mitigating techniques? And unfortunately, yes, there are by use of fragmentation. So when we have a closer look at the Kali Linux, at this module, when we just open it, and when we are looking here at the optional, which we have here, we have option -H, F, D, and so on, add a hop-by-hop header to bypass RR-guard security. So he implemented these mechanisms to bypass this RR-guard security feature, and you can use a destination header. You can use a fragment header or a hop-by-hop header. So he's using extension header to enforce the fragmentation of the packet. So the packets get larger than 1500 bytes. So he has to fragment it, and the switch does not reassemble it, it just forward it, and he can't, because the upper layer protocol information, so the ICMP header is only present in the second fragment, and the switch is only looking at the first fragment. The switch says, well, okay, I have here a fragment. This doesn't look like a router advertisement, so I'll let it pass, but he does not check the second fragment. Because this check is quite hard to implement in hardware. I mean, of course, you can implement it in software, but it's expensive CPU-wise. And what is better, when the switch gets DOSed, doesn't help at all. So the switch just validates the first fragment, but there are no upper layer protocol information in the first fragment. So the second fragment gets through without any verification. And with this, we can easily, unfortunately, circumvent this, all these security features. And this is not limited to router advertisement guard. I will show you what other kind of features Cisco implemented in regards to first hop security, but it's all, for all features, it's the same problem that they all can be circumvented by using fragmentation. So just to give you an idea how this works, we just say, okay, what we want to use a large destination header to enforce the fragmentation so that the upper layer protocol information is stored in the second fragment. That's all we want to do, and we just say, yes, please use this destination options header, and we are good to go. So is he still capturing? It looks like it. I'm surprised it didn't crash by the amount of router advertisements he was sending. So I just start it again. So ETH0. So and I will just do it very quickly, just to give you an idea, okay, how these packets look like. Otherwise, I could run into the issue that Wireshark is crashing at least the GUI because just of the amount of packets it is sending. So, as you can see here, we see now a couple of fragments. Well, unfortunately, Wireshark is interpreting it as a malformed packet. But as we can see here, here's the router advertisement. Or more interestingly, we have here the IPv6 header. And what we see now, we have an additional destination option header, which basically, it only gets padded. And the only reason he is doing that is to enforce the fragmentation so that the upper layer protocol information are not present in the first fragment, but in the second fragment. And as we can see here, this router advertisement consists of, in total, 3 fragments. And as the switch is only evaluating the first fragment, and the first fragment does not have any information that it is a router advertisement, he will just he'll let pass any subsequent fragments belonging to this packet. And also the router advertisement. So, and as we can see here, he's only padding just to enforce the fragmentation. And then potentially in the third fragment, we have the ICMPv6 header with type 134, where it is, where we can see it is a router advertisement. So I will close this and just let it run a little bit longer and see. That's interesting. Not Not that I know of. Maybe he did it automatically, but maybe I just did something wrong. Oh, well, it seems that I have installed the newest image just yesterday, and it seems that they have implemented this now in software so that he is also looking at the second or third fragment. Well, but memory allocation failed. Yes. When we look at the process, IPv6 input process, well, this doesn't look that good at all. So it seems they have changed something, which I wasn't aware of, honestly. But it seems they have now some issues in their code. Because the memory allocation failed is never a good sign on a networking device. And so we should be able to replicate this behavior. Wrong virtual machine. So yes, as soon as I started, oh my God, I don't have any free memory. Caused memory fragmentation. So this seems to be a bug in the iOS version. Yeah, it's 15.2.2E1, so dating November 2014, and I think it's the latest image available for this platform. So that's an interesting point I wasn't aware of. So it seems that the switch is now processing the fragments, and he will drop the fragments because, as we can see, it does not have any impact on this machine. Forward as just no. So, okay, they changed something. Interesting. I have to validate that because I wasn't aware of that. But, well, yes, that the switch is running into memory allocation failures is actually also not a good sign. So they might have some issues now in the code as they are validating more fragments. So, and this should, so potentially, okay, yeah, it's running at approximately 70 to 80%. Interesting, I have to validate that. So, but the basic problem still remains that with the use of fragmentation, we can circumvent, it seems, all these features. Router advertisement guard, and then they had phase 2, which implemented DHCP-v6 guard and NDP snooping. NDP snooping is the equivalent to dynamic ARP inspection, so that the switch is validating the neighbor solicitation, neighbor advertisement packets to prevent the neighbor spoofing. And in the meantime, at least in the Cisco space, you have good support on your current access layer platforms. Like 3560, 3750, 2960. So at least you are running a more or less up-to-date image. There is an overall good support for these platforms. And the DHCP-v6 guard behaves basically like the counterpart in the IPv4 world, where DHCP server packets get dropped on an interface where this feature is enabled, so that an attacker cannot send DHCP server packets so that the clients do not configure an address from the malicious range. Yeah, and here we see this NDP snooping feature. Basically, what the switch is doing, he is building, through normal operation, he is building a so-called security neighbor binding table, where the addresses he has seen through snooping the packets, the multicast packets, will get installed in this IPv6 neighbor binding table so that he knows, okay, this address, this link local address has this link, this MAC address and is connected to gigabit Ethernet 1.15 in this specific scenario. And this address was learned by the neighbor discovery process. And when I try to spoof neighbor advertisements with a false MAC address corresponds to one of these IPv6 addresses, the switch just drops the packet because they say, just wait a second, I do not have this association in my neighbor security binding table, and it just gets dropped. So basically, the same principle like in the IPv4 world with dynamic ARP inspection, where the switch is validating the information in the ARP packets. In the IPv6 world, he is using it, or he's validating the neighbor advertisement packets by building this binding table and then validating the all neighbor advertiser, neighbor solicitation packets. So I'm running out of time, so I will be a little bit quicker. Here's just an overview for you. All these slides will, of course, be publicly available after the presentation or after the conference, so that you see, okay, which actual FHS feature is available, starting with which iOS version. Yes, we already covered this, that they work as expected, but they can be circumvented with the clever use of extension header. So, and the IETF and Fernando Gont thought about, okay, how can we fix all those issues? And the answer to that, and the only answer to that, is RFC 6980. Security implications of IPv6 fragmentation with IPv6 neighbor discovery. Basically, what this RFC boils down to is that it forbids the fragmentation of all neighbor discovery related packets, be it neighbor solicitation, neighbor advertisements, router solicitation, or router advertisements. So that even when me as an attacker is sending a fragmented router advertisement and it gets forwarded to the client has to discard the packet and does not have to process it. But as you can see, it was released in August 2013, and I'm currently, I don't know if it's already in the Linux kernel. I'm honestly not sure about that, but at least it's not in Windows operating systems, maybe with Windows 10, but I haven't heard anything about that. So, and this is the only, from my perspective, the only thing we can do to prevent the issue with bypassing these security features by the use of fragmentation. From a networking device point of view, as we can see, well, the switch seems to validate the second and the third fragment, but this results in any memory allocation failures for the IPv6 input process, which shouldn't happen. We see the CPU load of the device is at around 80%. So this is the only thing, from my perspective, which really solves the issue with the fragmentation. And hopefully every vendor will implement this RFC. And if you are responsible for coding an IPv6 stack, please do us a favor, read this RFC and implement it. I mean, yes, well, of course, you could also work with ACLs, but this gets ugly really fast because you have to apply all these ACLs on every port, and you generally, on a large scale, you don't want to do that. So you could potentially do it, but at least from my point of view, not in an operational feasible way. So, to summarize, as we have seen, we have a different attack surface in the IPv6 world than in the IPv4 world. There are quite some attacks which are equal in comparison to IPv4. We are this is a relevant point. We are vulnerable to all these to those kinds of attacks, even if you do not use IPv6 in your corporate environment. It is enough that when your IPv6 stack is enabled, that's sufficient to be susceptible to those kind of attacks. And at least in the Windows Microsoft space, deactivating IPv6 by using a registry entry is not a feasible solution because Microsoft indirectly threatens you. Well, yes, you can do that, but if you open a support case, we may ask you to activate IPv6 because Microsoft says we are testing all of our software. We are testing with an enabled IPv6 stack, and when you disable it, we cannot guarantee for the correct functionality of different services. So, from a corporate perspective, when you have a huge support contract with Microsoft, deactivating IPv6 is not a feasible option. Yeah, and as we have seen, defending against those link local attacks today is pretty hard due to potential hardware limitations of our access layer switches, depending on which device and which version you are using, and as we can pretty easily circumvent those features. I'm not sure why it's not the case with this one. I have to follow this up, and I will put in some additional slides based on my observation or what I can find out. So we have to see how things develop in the future. And when you're, as I said, when you're responsible for implementing IPv6 stack, please do us all a favor and implement RFC 6980, and I hope that it will be integrated in all operating systems soon, but time will tell. So this concludes the basic attack and mitigation strategies presentation. If you have any additional questions, I will be around here in the venue the whole week. So just feel free to stop by and ask anything you want. We can, of course, chat about anything other if you would like. Besides that, I hope you have now a pretty good insight about some basic attacks and security issues we have, especially on the local link and potential mitigation strategies. And with this will be my last words. Enjoy your lunch. Enjoy the IPv6 Security Summit. I hope you have great 2 days or more when you are here for the whole week. Enjoy your lunch, and then we will see us during the conference.